Assalamu alaikum. This is MD Tanjil Sarkar, Postdoctoral Research Fellow, Faculty of Engineering, Multimedia University. Here I presenting my paper named Investigation of Optimal Perturbation Signal for Multivariable System under Moderative Control. The presentation outline is in the introduction objectives, then input signal design for MPC, investigation of implicit spectrum design for closed loop identification, then conclusion. Introduction. System identification is a methodology for building mathematical model of dynamic system using measurements of systems inputs and output signal. Figure 1 is represent the process of system identification. The basic idea of MPC is to predict the future behavior of control system over a finite time horizon and compute an optimal control input that while ensuring satisfaction of given system constraint minimize and a priori defined cost function. Figure 2 is representing the basic concepts of MPC. Figure 3 is represent the block diagram of a message system where 3 inputs and 1 output, and figure 4 is the MIMO system where 2 input and 2 outputs. Objectives. This research investigates the selection of optimal perturbation signal for multivariable system under MPC to enhance control effectiveness. 3 dissimilar methods to shape up the implicit spectra has been tested with 3 different signal-to-noise ratios. The scenarios with and without constraint in the closed-loop settings are also studied for multivariable system. Input signal design for MPC. Flood spectrum. The flood spectrum signal is defined by U flood, a summation of A cos twice phi fkt plus phi k, where A is the positive constant and fk and phi k are the frequency and phase of harmony of k respectively. F is the number of harmonies. This signal can be generated using the time frequency swapping algorithm in order to minimize the crest factor. Properties of flat spectrum. Uniform excitation across frequency band of interest, very useful when we do not have any prior information about the system. For non-parametric identification, we can use flat spectrum. Input signal design for MPC. Moves to signal. The moves to signal U moves to the flat U flat signal is shaped through the filter operation given by U moves equals to X OFT U flat, where U moves to and U flat are the Z transformation of U moves and U flat respectively. XOFT XOPT is the shaping filter provided by MOS2. Properties of MOS2. Only one type of input spectrum is supported by MOS2. It is the MAFIR spectrum. Only supported fixed controllers. The optimality criteria function minimize the determinant of covariance matrix, impose upper and lower bounds on the excitation input and output spectra. Optic spectra. The optic spectrum can be generated using by replacing the flat amplitude A with the optimum amplitude A of T. Obtained from the opt-exit algorithm. The opt-exit signal is defined by U opt-exit summation A OPT cos twice pi fkt plus phi k. The signal can also be generated using the time frequency swapping algorithm. Properties of opt-exit. To generate the optimum input power spectrum for measurements of transfer function, it optimizes the implicit spectrum of the multisign. The dispersion function is utilized in the algorithm. Investigation of implicit spectrum design for closed loop identification. An example for two input low pass system in closed loop is chosen for equation 4 and equation 5, where signal period is n equals to 60. The excited harmonics are set from 1 to 48. Figure 1 shows the input spectra for the ideal design, where represent the two mixture of opt-exit signal. In this figure, the highest magnitude of the system G1 and system G2 input signal are for opt-exit spectra are at harmonics 12 and harmonics 1. An example for two input low pass system in closed loop without constant. In this figure, The clearly improved mean of maximum error approximate 24.4% lower. For the case without constant, error are typically higher at points where the frequency response magnitude of the actual system is higher. In this particular one, the operating signal gives very low error at low frequency, showing that the steady state gain has been identified with high accuracy. An example for two-input low-pass system in closed loop with constant. In this figure, we can see the rate of change of the control signal was limited during a simulation. The rate of change of the control signal's upper and lower bounds is set to minus 0.03 to plus 0.03. Errors are typically lower at points where the frequency response magnitude of the actual system is higher. The parameter estimates are treated as a compromise between obtaining a high degree of accuracy in the model frequency response and obtaining a high degree of accuracy in the noise model. Investigation of amplitude spectrum design for closed loop identification. An example for two-input bandpass system in closed loop is chosen where the signal period is n equals to 50 and excited harmonics are set from 1 to 20. For figure 8, we can see the size of system G5 input signal for the most spectrum is maximum at harmonics at 4. An example for two-input bandpass system is a closed loop without constant. In this figure, we can see the rate of change of the frequencies covered by the excited harmonics is zero point 0.52 radian per second to 10.47 radian per second with a sampling frequency of 10 Hz. Outside of this range, the error is higher in relation to the system gain while it is minimal inside. Both of the real and estimated system frequency response are almost identical and their inaccuracies are minimal. Comparatively to the magnitude of system G5, the magnitude of system G4 offers a smaller error. An example for two-input bandpass system in closed loop with constant. A simulation was carried out with constant of amplitude of control signal. Amplitude of control signal is determined by the operational range of the plant input signal. The upper and lower limits of the control signal are also set from minus 0.25 to plus 0.25. The frequency response of the actual system and the estimated system are matched for all systems and their errors are small. In low frequency and larger the higher frequency, respectively. The magnitude of system G4 provides a lower error comparatively from the magnitude of system G5. For system G4, the error comparatively lower than the without constant case. For system G5, the error also relatively lower than the without constant case. Conclusion: for two input and three input low pass system, the operator signal combination has the lowest error in the frequency domain. However, the two input and the three input bandpass system, respectively, the flat most two and flat most two signal combination offer the lowest error in the frequency domain. Additionally, the closed loop situation with and without constants are examined, and it is discovered that for both two input three input system the frequency response of the state system and actual system are closely matched. Future research ideas look at iterative system identification in which the input signals are alternate iteratively in accordance with the current estimate of the model parameter and the amplitude spectrum design of perturbation signal for multivariable system in closed loop setting. Thank you. Here have some reference for this paper.